on to units of measurement. A lot of people do not like the metric system. They're intimidated by it. They don't want to deal with it, which is a little bit silly for a couple reasons that we'll talk about here. One is that only the United States and a few African countries still use the English system, which is the name of the system that we use, right? Incidentally enough, England does not use the English system anymore, but this is not as complicated as you might think. Your money system is metric. If you know that there are 10 dimes in $1, right, you're using the metric system, right? Our money system is metric in its basic system. Also, if you know that there are 100 cents in $1, you're using the metric system, right? Because what are these numbers referring to? Right? They're referring to, sorry, I can't see this very well. They're referring to base 10 numbers, right? You know that there are 10 dimes in a dollar, DI, right, referring to 10. 100 cents, as in century, referring to 100 years. So the metric system is not that far off of what we use on a day-to-day basis. It's not that bad. And the last one I'll bother you with. If you know that there are 10 years in a decade, right? 10 years in a decade, you know the metric system. You might not be hyper aware of the English to metric conversions, and that's not that big of a deal because you can just look those up. But you do know the basic base 10 system of the metric system. Talking about units of measure in general, it's a quantitative observation, right, which means a number, observation or measurement, and it is always going to consist of two parts, right? The number and a unit. The number and a unit. Two parts, number and unit. Now, on actual exams, if you simply provide the number and you don't provide the unit, there's a really good chance that you're not going to get credit for that particular answer. You might get partial credit because you set that problem up correctly or appropriately, but in terms of the point that's awarded for the final answer, you're putting yourself in a position where you may not be awarded that point. So make sure that when you are boxing out your answers, when you're doing your calculations, when you're relaying your final response, make sure that you always have a number and a unit. So this metric system, which was created in 1960, was an international agreement that was reached to set up a system of units so that at the very least scientists everywhere could better communicate measurements. La Système International, right? It's French, right? So that's why the international system is SI, it's the SI system. Whereas when we say the international system, really you're saying the I word first, the S word second. But because it's French, they're a little bit they're backwards. Système International, right? So SI. This system is based upon derived units, right, from the metric system. And so we have one unit, 2 base units, 3, 4, 5, 6, and 7 fundamental or base units for the SI system. You've heard of probably all of these, right? The kilogram, the meter, the second, Kelvin, amps, moles, even the candela. Right? If you've ever looked into flashlights that are a little bit more on the high power side, they're going to have a candle rating, right? 1,000 candles, 100 candles, or whatever. But that refers to luminous intensity. And so these 7 fundamental units can be combined through multiplication or division in a huge number of ways to create every other unit that is known. So over here on the right, we have some very common units. So for example, 1 dime is about 1 millimeter thick, right? A quarter is about 2.5 centimeters in diameter. The average height of an adult man is 1.8 meters, right? These are all examples of length because they find their base in the meter, centimeter, millimeter, or meter itself. For mass, right, it's going to be the kilogram is the base unit. We can change that to the scale that we find most appropriate. A nickel has a mass of about 5 grams. Notice it's not a kilogram, right? It's just regular gram, but it's still mass. 120-pound person has a mass of about 55 kilograms. And then for volume, a 12-ounce can of soda, right, normal size can, has a volume of about 360 milliliters. And then we have our prefixes. Now they're not blue because I can only print in grayscale, but what I've indicated here, these are the ones that you really want to be familiar with. Mega, kilo, hecto, deca, deci, centi, milli, micro, and nano. Several of these you probably already know from using some sort of computer, right? When you're talking about the size of a file, the size of a hard drive, you typically talking about tera, giga, mega, maybe even sometimes kilo you still talk about. This actually used to be a pretty big deal when I was really young. A kilobyte was a pretty decent amount of memory. Not so much anymore. But when you go a decimal, right, like deci for decimal, right, 0.1, centi, milli, micro, nano. Typically, that's about as far as you need to go. If there's any need to go any further, typically the AP exam will actually give you that information before you move forward. So if you can familiarize yourself with these things that I've indicated here, you'll be in good standing. Let's move on to volume here. Volume confuses a lot of folks, and so we have our diagram here over on the right. Volume is derived from length, and so what we mean here is we consider a cube that is 1 meter on each edge. It is a cube, right? So it is 3-dimensional. Okay, it's 3-dimensional. So on each edge, there are 3 edges. Each edge is 1 meter. And so that creates a 1.0 cubic meter. So this is 1.0 meters times 1.0 meters times 1.0 meters. That creates 1.0 meters cubed. That's fair enough. But realize when we take an equivalent measurement that uses a different unit, like here we're going from, we're going to substitute the 1 meter for 10 decimeters, right? Remember decimeter is 1/10. So it's 1/10 of a meter. So in order to be 1 meter, we need 10 of the decimeters. If we're going for 1 meter cubed, it's 10 decimeters cubed. If you guys remember from math class, if we're going to cube something inside parentheses, not only are we going to cube the unit, we have to cube the other value as well. So it ends up being 10 cubed decimeters cubed, and that ends up being 1,000 decimeters cubed. Now, 1,000 decimeters cubed is the same as 1,000 milliliters, because 1 decimeter cubed is 1 liter, which is 1 L, right? It is slightly larger than 1 quart as well. But remember that 1 decimeter cubed is 1 liter, which is 10 centimeters cubed, right? When we go 10 cubed, centimeter cubed, that's 1,000 centimeters cubed. That's 1,000 milliliters. And 1 centimeter cubed is 1 milliliter, which is the definition of 1 gram of H2O, right? And specifically at 4 degrees Celsius, if you want to be super picky, which right now I don't want to be. Next, mass versus weight. Now, I, just like a lot of people, are very guilty of using these two terms interchangeably. They are not actually the same thing. Mass is measured in terms of grams or kilograms, right? That's the fundamental unit in the SI system. Mass is a measure of the resistance of an object to a change in its state of motion, meaning it exerts or exhibits inertia. It's the quantity of matter present. The more matter you have, the more resistance there is to changes in its state of motion. Remember the first law of thermodynamics, or should I say the third law of thermodynamics, is that an object in motion tends to stay in motion unless acted upon by an outside force. An object at rest tends to stay at rest unless acted upon by an outside force. So that's what we're talking about. Resistance to a change in its state of motion. If it's at rest, right, it wants to stay at rest, and it's going to resist a change in that state of being at rest. Or if it's in motion, it's going to resist changes in that motion, whether it's acceleration or deceleration. And that's what we refer to as inertia. Weight, however, is measured in newtons. It's actually a force. Okay? This is how much matter is present. This is a force. It's the response of mass to gravity. Right? Gravity is something that accelerates items that have mass, that are composed of matter, towards a center of mass. Right? Now, the reason that we use these terms interchangeably is because all the measurements that we do are going to be made on Earth, and so the acceleration due to gravity is going to be constant for the most part, at least for sure, with regards to how much precision and accuracy that we use in our lab. Although technically they're not used interchangeably, oftentimes we weigh chemical quantities. We don't necessarily mass them, but truly speaking, we should mass them. We mass them, and so because of that, we're going to use a balance, not a scale, because a balance compares a mass against another mass, right? Whereas a scale is going to weigh something. It's going to measure the force that gravity is putting on that mass. Let's finish up this small portion with gravity. Gravity varies with altitude here on the planet Earth. It truly does, but not to an appreciable amount. You're going to have to go up several miles before you start to experience any real change in your actual weight, right? Because the force of gravity is an inverse square law, which means the further you get from the Earth, the weaker the gravity of Earth will be on you. But the closer you are to the center of the Earth, the stronger that gravitational field will be, since it originates from the center of the Earth. Now, every object has a gravitational field. As long as you're on the Earth, they are massed since the Earth's field is so huge, right? So you have a gravitational field. I have a gravitational field. The desk that you may or may not be sitting in has a gravitational field. The computer that you may or may not be sitting in front of has a gravitational field. However, it's so small, those gravitational fields are so small that you can't perceive them. You, as a human, you're designed to exist on the Earth, and the Earth is so much larger than those objects. The gravitational field of those individual objects pales in comparison to the gravitational field of the Earth. Therefore, you can't actually feel it, because the strength of the gravitational field is proportional to mass, right? This is the proportional, right? That Greek alpha is proportional to mass. So the more mass an object has, the greater the gravitational field will be. That's why Earth has so much more gravity than, say, you or I. So, have you ever seen astronauts in space that are quote-unquote weightless, since they are so far removed from the center of the Earth? But notice that they're still moving, right? They're still being drawn to stuff. There's still gravity going on. It's just not Earth's gravity. When you really pay attention to how those astronauts are moving, they're actually typically going to be moving towards the sides of the ship, because in that system, the ship, the shuttle, is the most massive object there, and so it's going to have the largest gravitational field. And so, unless they're doing something to keep, from floating that way, they will actually move constantly towards the walls of the ship. And you see them constantly in video having to push themselves away from the walls of the ship. And if they're in the middle of a particular area, you'll actually see astronauts be drawn towards one another, because they are the strongest gravitational fields around.